Everybody's so quiet today. Oh, all right. Well, I have 1 o'clock. Jack, are you ready?
Yep.
All right. So it's my pleasure next to introduce Jack Calcut from Oberlin College, who will be telling us about Mazur and Jester 4-manifolds.
Thanks, Greg. And I thank all the organizers. It's really nice to be at a conference again. It's been a while. So this is joint work with my student, Alexandra, who is now at the University of Michigan. So a little background here. Contractible manifolds are going to come up. Whitehead found the first non-trivial contractible manifold. It was the open 3-manifold. Then around 1960, independently, Mazur and Po found compact contractible 4-manifolds, other than the 4-ball. About 10 years later, Cervera, but this is work of others, including Gonzalez Acuna and several other people. But in each dimension, n at least 4, there's a non-trivial compact contractible N manifold. And I just remind everybody that compact contractible manifold has a homology sphere boundary. Another notion that's going to come up here that motivates things is a splittable manifold. An open splitter is a manifold that's the union of 2 copies of Rn that meet in a copy of Rn. And a closed splitter is a manifold that's the union of 2 copies of a disk that meet in a disk. So of course, Rn is an open splitter and Dn is a closed splitter. And the interesting question is, are there other manifolds? And Glaser exhibited those for dimensions 4, 5, 3. More recently, splittings come up when Gabai showed that Whitehead's 3-manifold admits an open splitting. And then Rick and Craig showed that in dimensions n at least 5, every compact contractible N manifold is a closed splitter. And then they used some sorts of boundary sum and took interiors to exhibit uncountably many open splitters. And then looked at Davis manifolds. Garrity, Repaz, and Wright showed that uncountably many, in dimension 3, uncountably many open splitters exist, and uncountably many open contractible 3-manifolds are not open splitters. So these dates are approximate because they did their work at least 3 years before this is when it was published. So Pete Sparks, in his thesis with Craig, exhibited infinitely many closed splitters in dimension 4. And then again, using sums and taking interiors, exhibited uncountably many open splitters in dimension 4. So this work of Pete Sparks is what prompted the work that's here. So in order to construct these manifolds, Pete made the following construction. He calls it a Jester manifold, building off the dunce hat, which is the spine of the Mazur manifold. But so this is a dotted 1 handle. So this is a 4-manifold that's a 0 handle, union of 1 and oriented 1 handle, and then with a 2 handle stuck on. And so here's your 1 handle, and your 2 handle is attached on this knot here called K. And the 2 handle gets a framing that's an integer. So this is actually a family of 4 manifolds, 1 for each integer little k. Each of these manifolds is contractible because this 2 handle goes around algebraically once. And Pete used these manifolds to construct closed splitters. He didn't use this manifold itself because there were some questions about it that he didn't answer, but he used some other work of Wright along with this manifold to construct his examples. And he was motivated to construct these examples by Mazur's manifolds. So Pete defined these manifolds and he asked, are any of these not the 4-ball? He wasn't able to answer that. And then he asked, are these different from each other? All right, so before we answer these questions, I'd like to just review Mazur's 4 manifolds. So these are the manifolds that Barry Mazur discovered in 1960. Again, it's a 0 handle union of 1 handle and a 2 handle attached. Again, there's a framing coefficient that's an integer, so it's actually a family of 4 manifolds. Each of them's contractible. If you take the product with the interval, you'll get the 5-ball. And Mazur showed that one of these, if you use the blackboard framing, which turns out to be -3 here, Mazur showed that one example is not simply, the boundary is not simply connected. In particular, that 4 manifold's not the 4-ball. And that's one of the very first compact contractible manifolds other than a ball that was ever discovered, along with Poinet-Roux's example, which was different. So I'll quickly review because this will tie into some things that we did. How did Mazur show this manifold had non-simply connected boundary? Well, the boundary is given by this surgery diagram. The 1 handle changes into a 0 frame component right here. So this is a diagram for the boundary. This knot has framing K and this knot has framing 0. There's your relations for the fundamental group, the Vertinger relations. So here's this group, and this is exactly what Barry Mazur did. He did these tsetse, well, first of all, a bunch of these relations cancel. You can just, eliminate a bunch of variables. Once you do the obvious things, you'll get this presentation. Then you make these substitutions and you get this presentation. Now, when K is -3, this term right here is going to vanish and it makes life simpler. And so this is exactly what happens. When K is -3, you get this presentation. A little tinkering around, you get this one, and then you introduce a new relation here that B5 is trivial, and so you get a surjection to this group. Then you introduce C and eliminate A, and voila, you have a hyperbolic triangle group. So this says that the fundamental group of the boundary of the Mazur manifold with the framing -3 surjects onto the 257 hyperbolic triangle group. In particular, the group's non-trivial. This was exactly Barry Mazur's argument. But in fact, all of Mazur's manifolds are non-trivial. So I'm just going to review a few proofs that all of Mazur manifolds are not the 4-ball. Mazur showed it in the one example. Laudenbach has a paper from 1979 that shows all of them are non-trivial. The only thing that's needed is Den's lemma and the loop theorem. Also, Achblut and Kirby in their paper around that same time in 1979, they mentioned that Eaton had a proof that all these Mazur manifolds are non-trivial. But I've asked Selman about it and he can't remember the argument. I haven't talked to Kirby. Eaton has since passed away, so I've tried to find this proof. If anyone's aware of it, I'd be interested in hearing about that. There's a modern proof that all of these Mazur manifolds are non-trivial. It uses property R in the Poincare conjecture, which seems to be overkill. But even this modern proof, you take that knot that we did surgery on, it's in S1 cross S2. You need to know the knot's non-trivial to even make this machine run. But once the knot's non-trivial, property R says you can't get S3. And so the boundary can't be simply connected by the Poincare conjecture. Here's another proof though. Alexandra and I computed the Casson invariant of all these boundaries of the Mazur manifolds, those homology 3 spheres. And it turns out, we used work of Matveyev and Polyak, that all of the Casson invariants are -2. So there's another proof that they're not the three sphere. We actually gave two more proofs that all of these boundaries are non-trivial. One, we take the fundamental group of the boundary, and Alexandra found this nice trick to introduce this relation here. We tried all sorts of things, by the way. A lot of times the group dies, but Alexandra found this nice trick to introduce this relation, and you get this quotient of the fundamental group. And then this group, its isomorphism type only depends on K mod 12 now. And so it's a finite problem to just check these 12 groups, and Magma finds surjective homomorphisms to permutation groups. But some of them are permutation groups on degree 40. Some of those are non-trivial homomorphisms that you wouldn't find yourself, but there it is. And here's another proof that all these groups are non-trivial. But it leads to a nice question. Okay, so start with the fundamental group of the boundary of the Mazur manifold. Motivated by what we saw earlier, A7 and B5, remember that triangle group we got out of it. So motivated by that, we just introduced these relations. And then we add a generator C and kill A, and we get this is a quotient of the fundamental group of the boundary of the Mazur manifold. And then you look at this group and you see that it's the 257 hyperbolic triangle group with one more relation in it. And so our conjecture is that this group should be non-trivial, at least when K is sufficiently large. I mentioned here that this element here, so this is the 257 triangle group quotiented by one more element, a power of an element. And this element right here is infinite order. It's easy to check that because the only elements in the triangle group of finite order are conjugate to these. And so the only elements of finite order have order 2, 5, or 7. And you can find homomorphisms from this group to permutation groups that carry this element to an element of order not 2, 5, or 7. In particular, this element, it's easy to check this element has infinite order. Okay, so summarizing. We've got this 257 triangle group quotiented by the power of a word. This word BC cubed has infinite order. So what happens? Well, when this exponent K plus 3, when it's 0, then you just have the 257 triangle group. When K plus 3 is small, namely 1, 2, or 3, so when this exponent is 1, 2, or 3, this group actually dies. It's trivial. So now introducing this extra relation with a low power kills the whole group. And then we conjectured that this group will be non-trivial as long as that power is at least 4. And we checked that with Magma up to 40. We even checked it higher, but we got everything from 4 to 40. So as long as this power is at least 4 and up to 40, this group is non-trivial. So then I asked Jim Howie about this, and he proved that as long as the power is at least 20, then indeed this group's non-trivial. So that proves our conjecture. We checked it with Magma for some values from 4 to 40, and Jim Howie showed it's true for exponent at least 20. And so indeed, this conjecture is true. Introducing this word to a power doesn't kill this triangle group. So that's our general conjecture. Take a hyperbolic triangle group. So we have 2 generators, these 3 relations. The exponents are at least 2, and it's hyperbolic. So the sums of the reciprocals are less than 1. So a standard hyperbolic triangle group. Pick an element in the triangle group of infinite order. Then we conjecture that when you introduce the relation W to the J, the group will be non-trivial provided J is sufficiently large. So that's a general conjecture. Where am I at on time here? 5 minutes. Okay. So all the Mazur manifolds have non-simply connected boundary. We just gave like 5 different proofs of that. Well, then the natural question is, are all those boundaries different from each other? I mean, they probably are. Alexandra and I showed that their fundamental groups of the boundaries are pairwise non-isomorphic for K between -200 and 200. We did this with magma. It was non-trivial. It took a long time. But that's about as big as we could get. And then magma starts dying on us. We did this by checking low index subgroups, and we abelianized the low index subgroups and compare those to each other. It was a huge computation. And we conjecture they're all different, but as far as I know, this is an open problem that all the Mazur manifolds are actually different from each other. I asked Salman about it. He says it must be true, but he also doesn't know of a proof somewhere. Okay, back to Jester manifolds. That was our main motivation, was Pete Sparks's question about the Jester manifolds, which are similar to the Mazur manifolds, but different. So Alexandra and I showed all the Jester with similar techniques to what we just did with Mazur. We showed all the Jester manifolds have non-trivial fundamental group their boundaries have non-trivial fundamental group. The Casson invariant, by the way, doesn't work here. All the Casson invariants of the Jester manifold boundaries vanish. So Casson doesn't work here. We also checked that these fundamental groups are pairwise non-isomorphic, but only in this smaller range, because these groups are more complicated than the Mazur manifold groups. The presentations are more complicated. Of course, we conjectured that these are all different as well, but we've been unable to show that. And that's it.
All right, let's thank Jack. Anybody have any questions?
Sorry, just a quick question. So the fundamental group of the Jester manifold is not like any like triangle group or something?
No, but we can, in some cases, get quotients that are triangle groups. And that's a common technique to show groups are different. In fact, triangle groups come up all over the place, and there are ways to try to show a group is non-trivial if you can find a quotient that a triangle group. That's why I think this conjecture is nice, because here our quotient was a triangle group with an extra relation. And we thought, hey, this should still be non-trivial. And I checked a ton of literature. I thought this should be known, but it turns out it's not. And it seems like a nice conjecture that if you take a triangle group and introduce the power of a word, that could be non-trivial, because those could be useful tools to show other groups are non-trivial.
Yeah, thank you.
Sure.
I have a question.
Yes.
Are there contractible 4-manifolds which are not balls but have boundary a 3-sphere?
No, well, that's unknown. I mean, not topologically, but smoothly, that's the 4-dimensional Poincare conjecture, or Schoenflies, right? If there's an exotic, it's open whether there's an exotic R4 that's smoothly collared at infinity. If there was an exotic R4 collared by S3, then you would shave off the end and get an exotic 4-ball. But so that's open in the smooth category, but it's in the topological category that the ball is the only one by Friedman.
Okay, thank you.
Yep.
Is anything known about the splittability of the Mazur manifold?
Not that I know of. So, Pete's the one to ask that, but from what I understand, Pete modified Mazur's construction in order to get something that he could split.
Yeah. Yeah, that was the original motivating question, I think, though. And nobody's figured it out, I guess. I just wondered if you knew something new.
No, I don't.
Yeah.
So the question is Mazur's manifold itself a closed splitter? And that was the motivation for all of this.
So in looking at all of these groups and using Magma to show that they're pairwise, non-isomorphic, are there any sort of patterns that emerge? You know, I don't know exactly, you know, when K is a multiple of 5, it's this kind of group, anything like that?
Yeah. In fact, we have lots of other ways to show some of these groups are non-trivial. And so for K congruent to certain things, it's easy. And then when K is congruent to other things, the groups are much harder to understand. So yeah, tons of patterns emerge.
Any other questions?
I have a question. So besides looking at the fundamental of the boundary, are there other sort of interesting invariants you guys looked at to distinguish between these manifolds?
So it's, I mean, we computed everything we could. If I recall correctly, the Floer homology didn't help. Selman suggested we should look at the contact invariant, which I haven't computed yet. So some of the major manifolds are Stein, as long as the framing is at least a certain size. And so for those, you could look at the contact invariant of the boundary. I'd be interested in any invariants anyone computed, or if you have ideas about it, I'd be happy to hear about them.
Okay, thank you.
Yep. I was hoping all their Casson invariants would be different, and they all turned out to be the same.
May I ask if you used gap, not only Magma? I heard there is a very sophisticated algorithm in gap which tells if group is trivial or non-trivial. So if it's non-trivial, then obviously that's what it is.
I haven't. I'll have to look at that.
Okay.
Magma has it. Go ahead.
Something published or it's work in progress?
Work in progress.
Mm-hmm.
Interestingly, we had two groups. So actually, Pete defined two different classes of Jester manifolds. And we actually showed they're the same class. Their knots look different, but we were able to find that the knots were the same. And the way we discovered that these knots in S1 cross S2 are the same is because we wrote down their fundamental groups. And I thought I was going to show they were different with Magma. But Magma couldn't distinguish them. Everything that we computed were the same. And then Derek Holt has a program in Magma that you say is isomorphic. And sometimes it'll tell you these finitely presented groups are isomorphic. And for our presentations, it worked. And it gave us an isomorphism, which gave me a clue on how to show the knots were the same. So just to advertise Magma's little command is isomorphic by Derek Holt. It actually, most of the time it doesn't work because this is an unsolvable problem, right? If two finite presentations are present isomorphic groups. But it actually worked for us.
And I second for that. I used in my one of the articles Magma to classify all homomorphisms between finitely presented groups up to conjugacy in the target. And GAP doesn't have this functionality, but Magma does, also by Derek Holt. That's useful.
All right, any other questions? All right, if not, let's thank Jack again. And the next talk will be in about 6 minutes.